Hello friends, welcome you all to the 36th lecture on functional analysis and its applications. In this lecture, we will discuss the orthogonal decomposition theorem, that is projection theorem. These are the contents of today's lecture. Further theorems on orthogonal complements and the orthogonal decomposition theorem, that is projection theorem. So, theorem: if M is a linear subspace of Hilbert space H, so that M is closed if and only if M equal to M double perpendicular. Proof: let M be subspace of Hilbert space H and let M equal to M double perpendicular, that is perpendicular of M perpendicular. Okay. So by theorem of lecture 34, that is in this theorem, we have discussed if S is a subspace of a Hilbert space H, then S perpendicular is a closed subspace of H. Here M is a linear subspace of Hilbert space H. Then perpendicular of M perpendicular is closed subspace of H. Therefore, M is equal to M double perpendicular is a closed subspace of H. Conversely, suppose M is closed subspace of H. Okay, then we have to prove M is equal to M double perpendicular. Conversely, suppose that M is closed subspace of H, then to prove M is equal to M double perpendicular. By theorem 1, part 5th of lecture 35, we have M is subset of M double perpendicular. Therefore, M double perpendicular is a Hilbert space. Suppose now that this inclusion is proper, that is M is not equal to M double perpendicular. Since M is proper closed subspace of the Hilbert space M double perpendicular, because here M is a subset of M double perpendicular, that is the Hilbert space here M double perpendicular. Now M double perpendicular is a Hilbert space and M is a proper closed subspace of M double perpendicular. Therefore, by theorem 2nd of lecture 35, there exists a non-zero vector Z0 in M double perpendicular such that Z0 is perpendicular to M, or Z0 belonging to M perpendicular. Okay, now Z0 belonging to M perpendicular and Z0 belonging to M double perpendicular. This implies that Z0 is the element of M perpendicular intersection of M double perpendicular. Since M perpendicular is subspace of H, therefore by theorem 1st, part 3rd of lecture 35, we have M perpendicular intersection M double perpendicular is singleton set 0. Okay. From equation 3 and 4, we conclude that Z0 is equal to 0. Okay. Because here Z0 is the element of singleton set 0, that is 0. This contradicts the Z0 is a non-zero vector. Therefore, M is proper subset of M double perpendicular, cannot be a proper inclusion. Hence, we have M is equal to M double perpendicular. Theorem 2. If M and N are closed linear subspace of a Hilbert space H such that M perpendicular N, then the linear subspace M plus N is also closed. Okay. Proof. To show that M plus N is closed, we have to prove it contains all its limit points. Let Z be any limit point of M plus N. In order to show that M plus N is closed subspace of H, it is sufficient to show that Z belonging to M plus N. Since Z is a limit point of M plus N, there exists a sequence Zn in M plus N such that Zn converges to Z in H. Since M perpendicular to N, therefore the subspaces M and N are disjoint. That is, M intersection N equal to singleton set 0. And so the subspace M plus N is the direct sum of the subspaces M and N. Consequently, each Zn can be uniquely written as Zn is equal to Xn plus Yn, where Xn is the element of M and Yn is the element of N. Consider two vectors Zm and Zn as Zm is equal to Xm plus Ym and Zn is equal to Xn plus Yn. Let us examine the norm of Zm minus Zn. Zm minus Zn is equal to Xm plus Ym minus here Zm minus Zn is equal to Xm plus Ym minus Xn plus Yn. This implies that Zm minus Zn is equal to Xm minus Xn plus Ym minus Yn. Okay. Since Xm minus Xn is the element of M and Ym minus Yn is the element of N and M perpendicular to N, therefore Xm minus Xn perpendicular to Ym minus Yn. Then by the Pythagorean theorem we have here two vectors, this and this, that is, we know that if we have two non-zero vector x and y, that is Pythagorean theorem, norm of x square plus norm of y square. Okay, so using this formula we have this one, square of the norm of xm minus xn plus ym minus yn equal to square of the norm xm minus xn plus square of the norm ym minus yn. Okay, or this can be written as square of the norm of Zm minus Zn equal to this right side. Equation 5. Since Zn is convergent sequence in Hilbert space H and it is a Cauchy sequence in H, because every convergent sequence is a Cauchy sequence. Okay, so we have Zn is Cauchy sequence. Therefore, M and N tend to infinity. So norm of Zm minus Zn square tend to 0, because here Zn is a Cauchy sequence, that is norm of Zm minus Zn converges to 0 as m n tend to infinity. Okay, so squaring both sides, this we have this one. Okay, so square of norm Zm minus Zn from 5, this one tend to 0. Okay, that is, this is norm non-negative, that is first term tend to 0 and also second term to tend to 0. Taking square root of both sides of this implies that norm of xm minus xn tend to 0 and norm of ym minus yn tend to 0 as mn tend to infinity. This shows that xm and yn are Cauchy sequences in m and n respectively. Since H is complete and m and n are closed subspace of a complete space H, therefore m and n are complete. Hence the Cauchy sequence xn in M converges to x in M and the Cauchy sequence yn in N converges to y in N. Now z is equal to limit n tend to infinity Zn. Zn is xn plus yn, that is this one equal to limit n tend to infinity xn plus yn, equal to, this can be written as limit n tend to infinity xn plus limit n tend to infinity yn. So from this xn converges to x, that is limit n tend to infinity xn is x, and yn converges to y, so this is y, and x is the element of m and y is the element of n, that is x plus y is the element of m plus n. Thus z is the element of m plus n. Therefore m plus n is closed. Projection theorem. This is also known as the orthogonal decomposition theorem. If M is a closed linear subspace of a Hilbert space H, then H equal to M direct sum of the M perpendicular. Proof. If M is a subspace of a Hilbert space H, then we know that M intersection M perpendicular equal to singleton set 0. Okay, already we have proved it. Therefore, in order to show that H is equal to M direct sum of M perpendicular, we need only check that H is equal to M plus M perpendicular. Now by theorem of lecture 34, M perpendicular is closed subspace of H. Because here M is closed linear subspace of a Hilbert space H, so already in this theorem we have proved M perpendicular is closed subspace of H. Also M is given to be closed subspace of H. Therefore, by the above theorem, M plus M perpendicular is closed subspace of H. Let us put N is equal to M plus M perpendicular. From equation 6, we see that M is subset of N and M perpendicular also is subset of N. Then by theorem, first part 4th of lecture 35, we have N perpendicular is subset of M perpendicular. Okay, because here M proper subset of N, then N perpendicular is proper subset of M perpendicular. Okay, this is already proved in this theorem of lecture 35. Again, also this, as per this result, this will be n perpendicular is proper subset of m double perpendicular. This implies that n perpendicular is proper subset of m perpendicular intersection m double perpendicular equal to singleton set 0. Thus, n perpendicular is singleton set 0. This implies that perpendicular of n perpendicular equal to perpendicular of singleton set 0 equal to h. Okay. Here n perpendicular is equal to singleton set 0. So, this implies that n double perpendicular, that is perpendicular of singleton set 0. It is already proved perpendicular of singleton set 0 is h by theorem part first of lecture 35. Therefore, n double perpendicular is equal to h, equation 7. Since n is equal to m plus m, perpendicular is a closed subspace of h. This implies that n double perpendicular is equal to n. This implies that n is equal to h because here n double perpendicular is h. Okay. So by equation 7, 6. Thus, n is equal to m plus m perpendicular is equal to h, because here n is equal to h and n is equal to m plus m perpendicular. Finally, h is equal to m plus m perpendicular and m intersection m perpendicular is equal to singleton set 0. This implies that h is equal to m direct sum m perpendicular. This implies that h is equal to m direct sum of m perpendicular. This completes the proof of theorem. In this lecture, we have discussed the further theorems on orthogonal complements and the orthogonal decomposition theorem, that is projection theorem. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Bachman and Lawrence Naresi. Second, introductory function analysis with applications, John Whaley and Sons, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Walter Rodin. Thank you.